Alright, so let's get started. So I'm Gael Marocco. So I'll be talking about the Scikit-learn. So that's a project that has been existing for a little while, but we started working on it 2 years ago. And the goal is to expose machine learning methods in a way that makes them easy to reuse and combine them. And so I'll be talking about what I call statistical learning, which is using machine learning methods with the goal of doing some kind of inference or learning something about your data. So this is somewhat related to what Chris presented this morning, so Pi and C, with a different focus. So Chris is a Bayesian. I'm going to be a frequentist just for the fun of it. But really, the point here is that we're interested in statistical estimation when there are a ridiculous number of parameters. So basically, you've got a finite number of observations and a lot of parameters. So you do have a big estimation problem. And I'll go a bit over this. So that's really the difference between Chris's presentation and my presentation. So that entails two compromises. One is computational power. We want things to be computationally efficient. We want to be able. I work with gigs of raw data. And also statistical compromises. We're not going to be able to estimate really complex stuff, and we are going to have to bias our estimators. So I'll go back to this. Oh, by the way, this is the first time I'm presenting this tutorial. So please interrupt me, ask questions. I probably have too much material. That's fine. I won't cover it. I'd rather have a discussion than just a course. So there's a lot of text that I won't be covering. I've added it so that you could have it. Alright, so we'll start with a problem setting. So first, throughout the scikit, we're working with data sets that are made of NumPy arrays. So I'm going to type a lot of things along, and I suggest you do. The goal is to have a code-driven tutorial rather than a concept-driven tutorial. So here we're shipping a few sample data sets. So from Scikit-learn, everything is going to start from Scikit-learn, and we're going to import the data sets. And we're going to use the iris data sets. So we're going to go datasets.loadiris. And we're going to look at the data. So it's iris.data. And it's a NumPy array that has a shape of 150 times 4. Can everybody get there? Does everybody have the scikits installed? IPython running? All this going? So this is an example of one of our what we call the data set object. So it's really just a 2D NumPy array. The first dimension is the number of observations, and the second dimension is the number of features. So in the specific case of the iris data set, we have observation for 150 irises that are described by 4 features, which is their sepal and petal length and width. So this is just a concrete example of a problem. We've got somebody who went in the wild and looked at irises and measured their length and width for their sepal and petal, and did this 150 times. So one remark, not every data comes as a 2D array. We'll have to work a bit on it. For instance, another example is the digits data set. So we can load the digits data set. And we can look at its image attributes. So it's an NumPy array And it's got around 1800 times 8 times 8. And if we do an imp show of the first entry of digits dot images, that's what we get. So what we have is a series of images of digits, and that's a 0. And they're 8 by 8. So what we're going to do to be able to use it with Scikit is that we're going to reshape this. We're simply going to flatten these images. We're going to forget their images. We're just going to take them as a vector of 64 entries. So our data is now these images that we reshape. So that's a bit of mucking around with NumPy arrays. I hope you're familiar with this. And now we have around 1800 observation of a 64 sized variable. And depending on your data, you will have probably to transform it in different ways. Right, so that's our data. That's an X variable, that's a 2D array. So now, almost all the objects that we have are what we call estimator objects. And what really defines them is they have a fit method that takes one of these data sets. So that's pretty much the definition of an estimator object. And so if we're interested in estimating parameters to draw scientific conclusions on them, well, so first, I should say, the estimator may take parameters, and these parameters can be given as construction keyword arguments, but they're also available as attributes of the object. Just fairly general, I'll be using this throughout the tutorial. But what we're really interested in, so that's the parameters of the estimator, of the model, if we want to talk in terms of statistical model. So the reason I'm talking about estimators and not models is that in machine learning, sometimes you use procedures to fit the data that are not based on a generative model. So I'd rather use the term estimator. And if the estimator estimates a set of parameters that describe the model, all the parameters estimated have an underscore at the end. So that's a convention that we have in the Scikit. So if you have a variable with an underscore at the end, it's a variable that's estimated from the data. That's for people who do statistics. Quite often you put a hat above the variable. That's the way we do it in the Scikits. All right, so that's pretty much what we need. We've got our data, our estimators. So first I'll be talking a bit about what's called supervised learning. So the goal of supervised learning is to predict an output variable from some observations. So the way we're going to formalize this is that the fit method is actually going to take two variables. One is the data set, X, and the other one is the variable that we're trying to predict. So some external variable. And the supervised estimators have, in addition, a predict method that takes unlabeled data and returns a prediction on what the associated Y variable would be. Does that make sense to everybody? If you're doing a linear regression, you're trying to regress a set of variables on another one. So the set of variables you're trying to regress is going to be X, and the variable that's your, what's the term in statistics? It's dependent variable?
Response variable.
Or response variable. So that's going to be Y. Right, so in supervised learning, we're often going to talk about two specific tasks. One is a classification task. So you're giving a set of observations, and you want to give labels to these observations, and the labels are not continuous variable. For instance, I have a set of irises, and I want to give their name. So suppose you know that the irises come from 3 classes. Let's say Setosa, Versicolor, and Virginica. Then given your data set, you're going to try to find out which observation corresponds to which class. So that's a classification problem. And the other one is a regression problem where you're trying to predict a continuous variable. Say, I'm going to try to predict the age of someone given some medical data, for instance. So that's a continuous variable. There's the big difference is between continuous variable and a set of discrete labels, classes. Alright, so let's just create this, get this iris data. So I have imported data sets, so I can just load the iris data set. And I can get my X variable, so my data, it's iris.data, and I can get my Y variable, so it's often called a target in machine learning. So I can look at what it's made of. It's a bunch of integers, and basically it's 0, 1, 2. So I've got the sepal and petal length and width, and the corresponding class label. So now we're going to try the simplest classifier, which is the nearest neighbors classifier. So basically, given an observation, well, I have a set of observations that are labeled. So classification has a fit procedure where it starts from labeled data and tries to learn how to label new data, and then it can have a prediction where given unlabeled data, it's going to try to predict the labels. So nearest neighbor is simply going to, when given new data, is going to look at what was the closest observation in the training set and use that one to predict. So one thing that's fairly important is that if you want to test with an algorithm how good it is at prediction, you should leave out data. You should not try to predict on the data that you've used to fit your algorithm. With the nearest neighbor, it's fairly easy to see this. I'm gonna be perfect at predicting with nearest neighbor, because if my test data is in my training data, I will have an exact match. So in machine learning, people often talk about training set and test set. So we're going to split data sets. So given the data set to experiment with my learning method, I'm going to split it in train and test data. This is ugly. All right. That's because the screen is small. So if you all have on your computer this file, I'm going to leave you run this example that pretty much shows you how to use a nearest neighbor classifier to try to predict the label of new irises, and I'm going to change this so that the image doesn't overlap with the code. Much better. Right, so here's the code. So I'm going to split my data set in training set and test set. So the naive way to do this would be to say, well, right, one train, I'm going to take, let's say, the first 90%. Or 80%. I need an error supply. Alright, so what's the problem with that? Yeah, that's exactly it. Well, that was just because I made a typo. Right, a bit better. What's the problem with that?
It's not random.
It's not random, which might not be the end of the world, but now if I take the remainder to do a test set, now that's really ugly. I only have one class in my test set. So I can have a really good prediction rule. Everything is class 2. So that's why here I'm permuting the data. It's not the end of the world if it's not random, but at least I'd like to split reasonably evenly my training set and my test set. So I gather you've all typed this. I'm going to copy paste it. Right. Now I'm going to import, so from Scikit-learn.neighbors, I'm going to import the neighbor classifier, which is nearest neighbor. I'm going to create an instance of it. So in machine learning jargon, KNN is K nearest neighbor. Alright, so it looks like this. So we can see that from the way it prints out, we can see it's different parameters, which I'm not going to go into, but I'd just like to point out that usually these things are reasonably well documented. So we're not going to dwell on all the parameters, that would just take too long. But you can find them simply by looking at the doc string. So it's question mark, not Python. And then I can fit it to the train data. So I need to get X and Y. Fit fits. So one remark is that fit always returns self, the object itself. And then I can try predicting on the test data, which I've not seen. I get this, so predicted class labels. So now I can check with the ground truth. So I made an error. 1. It's not too bad. I've just taken a random algorithm and tried it out on the data set. Alright, so we'll come back to this. So this works reasonably well. We've got 150 observation, 4 features. So it's actually a fairly low dimensional problem. We've got much more observation than features. So to get a bit of an intuition of the problem, suppose we're doing nearest neighbor prediction with only one feature. And the values of this feature range from 0 to 1. And we have n training observations. We're basically paving the 0, 1 space with, best case, we're paving the 0, 1 space with observation. So now, given, so I asked if there was a, yeah. Got my 0, 1 space. Best case, my training set is evenly spread through. And I can say which class. each one of these observations are. If a new data set comes in, it's going to land somewhere. It's not going to be too far from an existing data, from a training point. Worst case, the distance to a training point is 1/n. So, unless my ground truth is really jagged, I'm going to get a good prediction. Now, if I have a lot of features, if I have 2 features, they all range from 0 to 1, I'm starting to pave the 2D plane. If I have p features, I'm paving a cube of dimension p. Now to pave this evenly, to sample this evenly, I'm going to need a lot of observations. A huge amount. I mean, it's good. If I want to sample this evenly, it's going to be exponential. So that is what people call the curse of dimensionality in machine learning. So it's basically, if you have high dimensional data, you are in trouble. You're going to need a huge amount of observation. And so this is what machine learning addresses through different ways. And I'll be talking a bit about this, how we can address this. And I'll first take the example of linear models. So the simplest examples possible. So we're going to work with yet another data set, because all the data sets that I've shown you so far, so the iris data set and the digit data sets, were all classification tasks. Right now I want to do a bit of regression. So we're going to load what's called the diabetes data set. So these are standard data sets in machine learning or statistics. So, yeah. So just to tell you, this data set is a set of 10 physiological variables, so things like age, sex, weight, blood pressure, or other variables that are measured on 42 patients. So that's the X data. And the Y data, the data we're interested in predicting, is an indication of the progression of the disease in 1 year. So that's a real problem. We've got data, and we're trying to predict how a patient is going to evolve. So I'm going to retrieve X and Y and split it in training test sets. So I don't have to shuffle this data because I know it's already fairly random. So I'm going to just leave out the 20 last ones. So I can check that I've done things reasonably well by looking at the shape of the arrays. Right, so I've got my data set with 20 left out. Right, so linear regression. Suppose I'm trying to do linear regression between a 1D X and a 1D Y. So this is basically fitting a straight line to my data. So to link back with the presentation this morning, it's a linear model. My data, my observed data, Y, is given by beta coefficients times X plus some observation loss. So I can estimate this using, for instance, PyMC in a Bayesian framework. So let's do this using Scikit-learn. So I'm going to create an instance of a linear regression. So it lives in a module called linear model. So I've got a linear regression here. It's got almost no parameters. fit intercept is basically telling the model, do I want my straight line to go through 0 or not? Do I have an affine model or linear model? I can fit my data. And then I can look at the coefficients. So I can look at all the attributes. So one of them is coefficient. And this is what I get. I get the coefficients. So I've just fitted a multi-dimensional X. So it's not just fitting a line. It's fitting a hyperplane. Just the same thing in higher dimensions. So I've got more coefficients. I've got one coefficient per univariate variable. So I've got 10 coefficients, plus an intercept. But we're not going to discuss much the intercept. So really we're fitting a hyperplane to the data. This is a linear model in n dimension. Alright, so we can, yeah.
So the intercept is where the y variable is when all the x variables are 0?
Yeah, that's it. Yeah, it's not exactly the opposite. So we can look at the error in prediction, and we can take, as an error in prediction, we can do the mean square error of the predicted value versus the real value on left out data. So I can predict using the predict method. So I'm going to give it the test value, so it predicts a set of values. I'm going to compare this to my data. And I'm going to take the mean square of this. So this can be seen as a goodness of fit measure on left out data. I stress that doing goodness of fit measures on left out data is important. So actually, there is a score method to the linear regression model or estimator that can be used to give a goodness of fit measure. And so it takes x and y, and it tells how much the prediction of the model fits x and y. So it's the explained variance score, which I'm not going to go in detail, but basically what you have to know is that 1 is perfect prediction, minus infinity is really crap.
So it's like a multi-dimensional algebra kind of thing?
Yeah.
Okay.
I'm not sure why people use this rather than R-square. If you're going to ask the question, I'm not sure. But that's the standard. I mean, do you want to comment on this, David?
This is the first I've heard of it, actually.
Oh, okay. Well, we had R-square, and some people came in and said, variance. We have a set of different metrics that I'll talk about later. But just one thing that's important is, given an estimator object, you don't know what the model is. You don't know how to judge whether it's predicting well or not. So every one of these estimators exposes a score. Well, not everyone. Nothing is guaranteed with a Scikit-learn. Things might have, well, the only thing that's guaranteed is that your object has a fit. But we try to have scores that basically expose a goodness of fit, and bigger is better. That's the only thing you know, but it allows you to compare out of a family of similar models that allows you to compare them. Similar models, that's the important thing. But if they're all regression, then they're all going to be exposing an explained variance score, and you're going to be able to compare them.
And so you said the range is 1 to minus infinity?
Mm-hmm.
So any finite value is going to look really good.
I believe 0 is chance. So if you do below 0, you're doing below than chance.
Oh, okay.
So you're predicting.
Okay, that's
the opposite of what should be predicted. So you really want to be between 0 and 1, and close at 1. Alright. So I said that we had a curse of dimensional problem that we would be trying to tackle it. So here's a bit of intuition. Suppose I have only a one-dimensional problem, and I have only 2 observations. I can't fit a linear model to this. I'm trying to learn 2 parameters from 2 dimensions. So 1 intercept, 1 coefficient from 2 observations. I can't do that. The problem is that any small amount of noise in my observation is going to induce a huge variation in my estimation. Can you see that here, the lines? So I'm trying to give an intuition. So we're not going to be typing this. I'm too lazy to do this. So one thing that's commonly done in statistical learning is to shrink the coefficients towards 0. Which means that, so this can be seen in a Bayesian point of view as I'm giving a prior on my coefficient. And my prior is that if I take 2 random values out of the blue, they're probably not going to be correlated. So my prior is that coefficients are 0. And so this biases the estimation. If I rerun this many times, and I average out, I'm not going to get the true value. I'm going to get something that is slightly shifted to my prior, but it reduces the variance. So this is what I've done here. I've put a slight prior, and I've just rerun. So adding a bit of noise, I've just rerun the estimation many times, and we can see that we're always below the real line, but we're closer. So that's something that's known in statistics as a bias-variance trade-off. If I have little data, I'm going to have a lot of variance in the parameters I'm trying to estimate. So I can bias my estimator to stabilize it, and in terms of decision making, it might be a better compromise. And the problem always is to choose the right bias versus a variance trade-off. So this kind of biasing is actually what's called a ridge regression.
I have a question. When you make that decision to trade variance for bias, and you said something after that this influences your decision making, how is that? Is it that you have too much variance or too much bias and you're on one side of the threshold or another?
Well, so if I want to do a decision on the coefficient, if I want to say, well, if the correlation is bigger than 0.5, then I'm going to stop this program. So I can, if I have a model, so I need a model to do this, but if I have a model, I can count the number of times I'm making an error on this decision, so basically the threshold at 0.5, and then I can tune my estimator to minimize this error. So this is model-based. If I don't have a model, we'll be looking at that later on. But this is setting the problem in a decision theory problem where it's easier to come to conclusions. Does that answer your question?
Yeah, we'll see when we get to the other question.
All right, so let's do this bias estimate. So as I said, it's called a ridge regression. So ridge regression corresponds to putting a Gaussian prior. So it's a maximum posterior estimate, putting a Gaussian prior on the weights.
0 mean.
0 mean. And there's a parameter called alpha that controls the amount of prior you're putting in. So let's do some plotting. So here I'm just doing a small for loop just to sample randomly a bit of noise on top of a linear model. That's not going to work because I need variables that were defined above. Sorry. Need these ones. So this is basically my ground truth. So X, Y. And test is left out data. I'm just going to add a bit of noise to my ground truth, to my data, and rerun the estimation. So this X is just X plus noise. So by the way, I'm actually adding some normal distributed noise. So this is fairly consistent with a rich model. So I'm fitting this new data. And then I'm plotting the prediction on the test data. And plotting the data, the raw data itself. Something stupid. This tutorial was supposed to be talk tested. Oh yeah, thank you. I'm going to fit it first. So, as you see, I'm just fitting it, and I'm using fit and predict. But so, as you see, I've not used my knowledge of the model. I know it's an linear model, but I've not used my knowledge of the model. I've just used its fit and its predict function. And the reason is we want to be able to treat models as black boxes to try out different models. So yeah, I've pretty much reproduced the figure I was showing you. So nothing new. I can rerun this with a higher alpha. If I rerun this with a higher alpha, I'll get the lines that are more biased towards the error and that have less bias. Right. Okay, so how do we choose alpha? Well, we can choose alpha to minimize the error. So, for instance, in terms of explained variance on left-out data. So we're going to do this on the diabetes data set because it's a reasonable size. And so we can try in a grid of alphas. We can try to see which one gives the smallest left-out error. I'm going to create a set of different alphas. I'm going to use a logarithm space going from 10 to the minus 4 to minus 1 with the 6 values. And I'm going to, each time I'm going to fit some train data from diabetes, some test data fit the train data, which I'm going to set the alpha parameter to a different one. I'm going to test the score on the left out data. And just do this for each alpha in my list of alphas. Alright? So as we see, we're getting a different score each time. And I don't have a curve of this. Well, anyhow, we see that, and the reason I don't have a curve of this is that this changes very little but we see that it goes through maximum here, and then goes down. So this is an example of the bias variance trade-off. If I put absolutely no bias, I get my unbiased estimator. If I bias it a bit, the error on left out data goes up a bit. If I bias too much, falls down. So that's another point of leaving out data. By definition, the unbiased estimator will always work the best on trained data. But you could be fitting noise. You could be fitting part of the data that is not reproducible. So introducing bias in this kind of estimator is also known as regularizing the estimator. And so we're going to see a different example of regularization. So what we've done here is that we've done what's known as shrinkage. We're shrinking our coefficients towards zero, decreasing their amplitude forever. Now, if we look at so the unbiased estimator, we look at how it works on David's data set. So it's fitting a hyperplane in dimension 10. So it's really hard to get an intuition on this. That's something to keep in mind. The intuitions that you have on low dimensions don't usually go to high dimension. But we can look at cuts in this n-dimension plane, 3D cuts. And in particular, we can look at features 5 and 6. So if we go back up to the unbiased estimator, where is it now? Here. So features 5 and 6. So 1, 2, 3, 4, 5, and 6. So the regression coefficients were minus 80 and 50. And they're reasonably big compared to others. So now if we look at these two variables and look at them with the raw data, basically I have a cloud of points which I've fitted with a hyperplane. Right? Does that make sense? The intuition that I have a cloud of points and I'm fitting a hyperplane through that. And we can see that they behave very differently. It's actually always hard to get good examples on real data, but I wanted to work on real data for this tutorial. So actually we can't see easily my point. So what I wanted to show here is that in one direction I could be choosing pretty much any angle, and I would still be fitting my data reasonably well. So my data was quite circular, and the other less. It doesn't show too well. So shrinkage, rate regression, is just going to decrease slightly the angle on every direction. On real data sets, most often, not every variables. When you have a lot of variables, not every one of them is relevant. You don't know that. If you knew that, you wouldn't be picking these variables. But chances are they're not all relevant. So what we can try to do is set some to zero. And so one way to do this is to use a lasso predictor. So we've seen the ridge. Lasso is a bit similar to ridge, but it can set coefficients to zero. I'm not going into math here. The goal is not to do math. You're welcome to ask questions if you want more, maybe at the break. So the lasso is a bit like the ridge, except that it will, during the fitting procedure, set some coefficients to zero. So let us create a lasso object. So it's still a linear model, so I'm fishing it from the same module, linear model. It also takes an alpha parameter. I'm going to put it at the same value. This. And then I can do the same thing that I did before. Vary the alpha to find the best alpha. Alright, So I just recalled what I had already typed. Okay, so I'm getting this, and there's an optimal somewhere here. So it's the fourth alpha, so I'm going to take it. Test alpha equal. And I'm going to fit the data with this given alpha. Okay, so now I can look at the coefficients that I learned, and some of them are 0. Okay, so it has shrank the coefficients, so biasing them, but biasing some of them all the way to 0. And if we go back to the plots I had made, one of the two is set to 0. And it's not obvious by looking at the value of the coefficients on the unbiased estimator which one it's going to be. So that's called a sparse estimator. It can fit, during the fitting procedure, it sets some coefficients to 0. Any questions on that? Right, so one thing that's important to stress is that lasso is a mathematical problem. It's not an algorithm. There are different algorithms to solve the same problem, and they're going to work better in different settings. So I'm not going to go over them. It's a bit off topic, but you can see this if you look at all the objects in the linear model. There is lasso and lasso-Lars. And there are two different algorithms to solve the same problem. There should be a C also. Yeah. At the end of the documentation of lasso, there's a C also lasso-Lars. And it just happens that the Lars works better if your ground truth is very sparse. If you're going to end up with very few coefficients that are non-zero, whereas the lasso object will work better if you're going to select a lot of coefficients. And so this is the kind of stuff, what I've just stated, which algorithm works better in which case, which is pretty much requires good culture of machine learning. So it's the best way to acquire this right now is to go to the documentation, the Scikit-learn documentation. I will not do this in this tutorial, and it's a fairly rich documentation. And so for each problem, you should, once you get an intuition of how it works on your data, look at the documentation. All right. So we've seen how to do regression using linear model. I can use this on the classification task. So if I have only two classes, I'm going to give a 0 label to one of them, 1 label to the other one, and we can fit. So if the data looks like this, I can fit a straight line to it. So why is this a bad idea? What's that?
Your binary data.
Yeah, but why is it not going to work?
You also
Make
can't
predictions
do
outside. You can make predictions outside the range of.
Well, I could always threshold my prediction. So here, I could have more data. If I gather more data here, my line is just going to go down. Whereas really, I'm not getting any more information on the difference between two classes, right? So the standard solution is to fit a sigmoid function here. The reason why this function is chosen is it gives a good optimization problem that is convex and tractable. but you don't really care about this. It's just to keep in mind that if you have a regression problem, if you have a classification problem, you don't want to be using a regression object, you want to be using a classification object.
Also corresponds to posterior probability of two Gaussian classes.
Yeah, there's a probability model behind this. So that's known as a logistic regression. So we can create a logistic regression object. Oh, and it takes a C parameter that right now I'm going to put to. So the reason I'm putting C to 10 to the power 5 is that it gives the amount of regularization, and if I put it very high, my model is not very regularized. So how do you know that? Well, once again, you look at the documentation, and it says that C specifies the strength of regularization. The smaller it is, the bigger the regularization. So I don't want any regularization. I'm putting a big C. This is unfortunately machine learning folklore. These people know very well what they're doing. I can't fight against it. We can't rename every single variable and change values for everything. I've been doing machine learning for only a little while, so I personally find this a bit challenging. That's just the way it is. All right, so then we can fit, and we're gonna. So you should still have the iris data set. So it's a classification problem, so we're gonna fit it using the logistic. And so now we can look at the coefficients. And there are just betas. So the sigmoid is applied on the linear model, and the coefficients are the betas here. So for an intuitive understanding, you can forget that there is the sigmoid, and you can just see this as a linear model, because inside the sigmoid you have a linear model. It's just not a linear regression. Right, so if we look at the decision function, so this is in 2D, so taking only two of our features. This is the three classes, and they're colored in three different ways. So these two are hard to separate visually, I mean. And we can see the decision boundary that's been learned by the model. So this is actually a three-class problem. So the way it works is it learns decision boundaries for one class versus all. So that's three. It's fitting three different problems, and then it's doing a voting heuristic. So that's how to go from a two-class problem to an n-class problem. Does that for you? Okay. And in the logistic regression, we can do so either shrinkage or sparsity simply by setting parameters on the logistic regression object. So Nel2 penalty is going to do shrinkage. And the Nel1 penalty is going to give sparsity. I'm not giving any mathematical explanation of why it works. If people are really interested in, we can go in it. And as I said, the C parameter will control how much regularization. And basically, so if I put a small c, therefore a lot of regularization, and I use penalty equals L2, I'm going to shrink my coefficients uniformly to 0. Whereas if I put L1, I'm going to have a very sparse model, right? So small c's with a logistic regression and say penalty equals L1 will give me sparse models.
You mean large C?
No, I mean small c's. No, it's... I know. If you understand the math that go behind it, makes sense. If you don't, it doesn't. All right, so let's do an exercise. So we've got the digits data set that I've introduced earlier. So just leave out 10% of it and try using nearest neighbor and a linear model, and I'll leave you choose which one to see how well you can predict left out data on the digit data set. So there is, if you click on that link, there is just something to get you started. Oh, and there's the solution. Don't look at it.